Okay, we're back and we're doing some circuitry, and this is kind of a neat little thing that we can do with Kirchhoff's rules. These are, if there are some such a thing as fundamental rules for basic circuits with resistors, it'd be Kirchhoff's rules. And one is for series, which has to do with voltages, and that just says that when you go around a series circuit, by the time you get back to the battery, you've used up all of your voltage. Okay, so we can write that mathematically as the sum of your voltage losses is equal to the voltage input that you have from your battery. For parallel combinations of resistors, we're talking about currents. That is, you don't lose current when you have a circuit and you split that line into multiple branches, which is really what parallel is. And so whatever your total current comes into this junction where that wire splits, in this case 3 different branches, the sum of those have to add up to your total. So I'm going to use these two rules and just kind of see where it leads. And in particular, we're interested in what happens if you want to try to find your total resistance of the circuit. Okay, so for example, I have just a real simple series circuit here, 3 different resistors, and they're connected to a battery. If we apply Kirchhoff's rule for series, what it says is the voltage of your battery is equal to the sum of the voltages of these 3 resistors. Okay, resistors get warm, they're wasting energy, and you lose voltage as you go across them. Well, how much voltage do you lose? Well, for a battery we have Ohm's, or for a resistor we have Ohm's law. Okay, so just basically your current times resistance tells you the voltage loss that you'd measure across a resistor. And so Kirchhoff's rule says that the voltage of your battery is equal to the current times resistor 1. Now in series you only have one path, so you have the same total current going through everything. So that voltage loss would be IR1. Then that current goes through resistor 2, and you have a certain amount of volts that you lose. And then that same current goes through resistor 3, and that would be the voltage loss on that resistor. And Kirchhoff's rule says that those have to add up to the battery. Now we can think about this as, on the left-hand side for your battery, your total voltage of the circuit, that's equivalent to saying your current times whatever your total resistance is. And then we still have the same thing on the right. Okay. Now because it's series and you have the same current going through everything, you end up with a rule that current drops out where you just add the resistors together to get your total or effective resistance for that circuit. Okay, so adding up all of your individual resistors in series will give you the total resistance that you'd actually measure if you had an ohm meter that is loaded and connected to your battery. Okay, so that's pretty straightforward. A little bit trickier, and not as straightforward, is when you put those same resistors in parallel and connect it to the same battery. So now you're going to have some total current, and we have to make use of the second of Kirchhoff's rules. We have to think about what happens to the current. Okay, well in this case, if these are 3 different resistors, in parallel you have the same voltage across each particular branch. Okay, so just writing down Kirchhoff's rule will tell you that your total current is equal to the sum of these 3 currents in the branches. Okay, now let's think about how can we rewrite these currents. How do you find currents when you have parallel branches like this? Well, if there's nothing else going on in the circuit, think about the positive terminal of your battery. Okay, that's at some voltage, and as you come along this wire, nothing's happened. You haven't lost anything since there's no resistors in our diagram. So each of these 3 points is at the same voltage as your battery. Okay, you haven't lost anything. Now, follow the negative terminal, which we generally would say is at 0 volts. And if you work your way backwards, okay, nothing happens, nothing happens. These 3 junctions down here are all at 0 volts. Okay, because again, there's no other resistors on that path. Everything down there has to have the same voltage. So each one of these branches, each of these resistors, sees a total voltage difference across them the same as the battery. Okay, so according to Ohm's law, current is voltage divided by resistance. So you have the voltage of your battery divided by R1, the voltage of your battery divided by R2 for that middle branch, voltage divided by R3 for that last branch. Now on the left-hand side, for your total current, that's equivalent to your total voltage of the battery divided by the total resistance of your circuit. Now since in parallel the voltages are all the same, that V drops out, and what you're left with is 1 over the total resistance is the sum of the reciprocals of each resistance that you have on the branches. Okay, so if we were to generalize this, in parallel, your total resistance is the sum of all of these fractions, all of these reciprocals on each individual branch. We'd have to add those up, and then to get the total, we'd have to flip over whatever that sum is, whatever that final fraction is. Okay, so in series, we just add resistors together. That's the easy one. In parallel, you have this crazy reciprocal rule. And what's cool about this is that these are just natural consequences. These pop right out of these Kirchhoff's rules, which are kind of fundamental to the circuits that we do in class. Okay, so I hope this helps, and I hope this allows you to see where these rules come from. And until next time, we'll see you later.